places. I'm very happy to know that there is an audience for our seminars, and we're of some value to Notre Dame. That's very important. So the seminar next week, and this week actually, there are going to be 2 Cornelians, so making 3 of us. Okay? And so the seminar speaker next week is going to be Professor Andrew Wilson from Operations Research and Information Sciences that will talk about GANs models for people in computer science, but they're not here, so please tell them that. Today, I'm extremely pleased to have sort of a second generation CICS affiliate, Professor Ilias Bilionis from Purdue University. He did his PhD in applied mathematics at Cornell. His undergraduate in applied mathematics in National Technical University of Athens, the same school as me, and has been out at Purdue for 4 years, I believe. So we're very excited to have him visiting Notre Dame, and I know he told me it's not going to be his last visit, so hopefully we will have him back coming soon. So he will talk. His presentation sounds very engineering. His background is not in engineering, okay? So he's a mathematician who is trying to become an engineer. And I'm an engineer trying to become a mathematician, so I don't know how things have worked out. But anyways, he will speak on making the most of your resources, how to design simulations and experiments to achieve your engineering goals.
Thank you for Professor Zabaras. Thank you for the invitation. It's really a pleasure to be here. Yeah, it's actually true. I'm trying to become an engineer, and the reason is money. It's just how it is. Just because of that, you'll notice that my presentation doesn't have a lot of math. It has a lot of math at the background that I'm not really going to show to you, but we can talk offline if you find anything interesting. So my goal today is to basically give you all the resources that you need in order to ask these questions. If I have expensive simulations, if I have expensive experiments, and I want to select which ones I would do, how can I do that? How can I pose this question in the first place? And the answers are relatively simple. They're based on one idea, basically, that you should use Bayesian statistics to quantify your state of knowledge about everything you have given the data you have, and that this is one idea that I want to just spit out right now. And the second idea is that you should really think about what you want to learn from your experiments or your simulations. What is your goal? Do you want to learn the response surface everywhere? Do you want to figure out where the maximum is? Do you want to find out what the probability of a rare event is? So once you know what you're looking for, then I will tell you how to turn that into math, and then spend like 6 months working on it. You put a PhD student on that for 6 months, and maybe they come up with an algorithm. But the ideas are quite simple. And I'll try to show you these ideas in the full generality. So this is my group. As you can see, it's not very diverse right now, but we're trying to get there. I have mostly male students, but I just hired one woman last week, and I'm very happy. But I didn't have a photo, so I didn't put her there. The research that the work I'm going to talk about is actually funded mostly. I mean, the core of it was funded by Professor Zabaras during my PhD, and I just continued on it and connected it with a few applications. And my funding comes mostly from NSF, even though NSF doesn't really fund any of the stuff that I am going to tell you about currently. Hopefully that will change very soon, hopefully in a week or so. Anyway, I'm very optimistic. We'll see. And a lot of enough funds are coming from Purdue Research Foundation, University of Illinois, a very small grant, data consultancy in India, and Ford with a question mark because I have to sign the check. All right, so here's what we do. We do uncertain quantification, and that's what I'm going to talk about, by the way. We also do human-machine interaction, and when I'm saying machine, I actually mean building, so how humans interact with the HVAC, and the lighting system of a building. And of course, why should you care about that? Well, the idea is you should care because if people feel uncomfortable, they become less productive. So the question is, what is the state of the room, the lighting condition, the thermal condition of the room that maximizes productivity? This is what we're looking for. And we're actually trying to come up with open office environments in which we can control the comfort delivery of each, we can deliver comfort to each one of the individuals. So imagine that we can actually design controls that give you and the person sitting right next to you a different thermal environment, control and personalized for you, so that we can squeeze the maximum amount of work out of you. That's the idea. And the other thing that we do is socio-technical modeling. Again, human-machine interaction is socio-technical modeling. So we have, again, building systems, and we are trying to explicitly model the human element of these building systems. And we have a recent grant from NSF on smart and connected cities, where we're looking at subsidized residential communities in Indiana that doesn't pay for their energy bill. And we ask the question, what kind of information should you give to these people in order to incentivize energy conserving behaviors? So how can you, without money, make a group of people become more energy aware? How can you develop a culture of energy conservation? We're just starting that, so I don't know the answer to that. And we're also doing, this is my favorite work at the moment. Maybe next time I'll talk about this, if you call me again. It's, we're working on the foundations of system science. So we're basically modeling how engineers design, and in particular how, what happens if you put a lot of engineers in the same place. So how can you, for example, take a company like Boeing or Rolls-Royce that design a complex thing, and so in this company, if you visualize the hierarchy of the engineers, the guy at the top, the business guys at the top, pass down requirements to the system engineers, who pass down further requirements to the subsystem engineers, and so on and so forth. And each individual engineer is doing his own thing, trying to maximize their own payoff. So they're not necessarily doing the optimal thing there is to do for the organization. So the question we ask is, what kind of contracts between the organization and the engineers align what the engineers do with the goals of the organization? So this is a game theoretic, if you like, model of how people, engineers put together, can design complex things, and it's actually a mechanism design problem. We have actually 2 grants just to do that, and it's really exciting. But we're going to talk about this. I have to advertise the new stuff. If you want to talk about any of that, probably you're not the right audience because I didn't put any of that in my abstract, but we can talk offline. All right, so today we're going to focus on UQ. So these are the UQ problems that we consider in my lab. Propagating uncertainty through models. So problem number 1, let's call it the uncertainty propagation problem. Characterizing the sensitivity of models to specific inputs, so doing sensitivity analysis. Calibrating models on experimental data, optimizing certain objectives that depend on complicated models under uncertainty. And our focus is on 2 things. Problem number one, how do you deal with limited experimental and computational budgets? So how do you solve these 4 problems when you have a finite amount of computational or experimental resources? All right. So I'm more interested in developing techniques that can solve problems with real limitations, like you have an experiment and you can do it 10 times. What is the best thing you can do, rather than developing things that I have to look for an application yet. And the other thing we're focusing on is high dimensionality. So all of these problems suffer from the so-called curse of dimensionality. When you have a lot of parameters, either design parameters or stochastic parameters, none of the techniques really work. And we are actively searching for new techniques. And final topic we are interested in, the twist, if you like, that we give is how do you fuse information from different sources. What if you have 2 or 3 different models that predict the same thing, but you can trust one more than the other, and of course the one you can trust more the most is the most expensive. What if you have models, in addition to the models you also have experiments? What if you have 2 or 3 experiments predicting the same thing? How do you fuse information from these different sources to, how do you most effectively or optimally allocate your resources to the different information sources that you have available? Now today we're going to focus on this, but the ideas on a limited experimental budget, but the ideas that we are going to develop are actually applied on the information fusion side. All right, this is one of the examples of the practical applications we're working on. So this is on permanent magnet motors, or electric machines, if you like. It's a type of engine, of electric engine. And our problem is basically to propagate certain kinds of uncertainties through Maxwell's equations. So we solve the electrostatics, if you like. We approximate the operation of the engine by electrostatics at different rotation angles, and we can, let's say, for a given set of operating conditions, we say let's put this machine operate at a specific temperature, giving us a specific average torque and so on and so forth, and we can measure the torque we get and the variation that we get in the torque, etc., etc. Now we're particularly interested in certain kinds of uncertainties. Of course, we're interested in manufacturing uncertainties. So imagine that every time you make the components of the machine, they turn out a little bit different. And the problem is very challenging because in most of the design work on electric machines right now, people will try to exploit the symmetry of the machine, and they just simulate using finite elements only part of the machine, and they use periodic boundary conditions to extrapolate what happens. But when you include geometric uncertainties, this symmetry breaks, and the finite element simulator that you need for figuring out what a machine with broken symmetry does, it's ridiculously expensive. It takes a full day to run a single simulation for a single, for just a single set of a specific geometric design. Now on top of that, the other thing that we have is uncertainties in the magnetic properties of the material. So the steel you use in the machine, you have, of course, as a designer, specifications for that kind of steel, but it's kind of steel, depending on where it comes from, the manufacturer that gave it to you, etc., comes with slightly different properties. And if you want to build something that is going to last for decades, you better think about the kind of uncertainties that you're going to face 10 years down the road. Maybe this steel manufacturing facility in China is going to close in 10 years, and you're going to have to buy from another one. It's going to give you slightly different steel. How do you make a machine that is robust to this kind of uncertainty? But the first place, you have to, this is kind of an uncertainty propagation problem, of course, in the background, but in reality, the very first problem is, how do you quantify this uncertainty in the first place? What kind of data do you need from the supply chains? How can you make like an intelligent estimate of this kind of uncertainty? Because if this is garbage, everything is garbage, and it doesn't really make sense to do anything. Another kind of uncertainty that you may have in these machines is operating conditions. So these things, you don't really know how your engine is going to be used. And again, if you want a useful design that is economically viable and is going to last a lot of time, you have to think ahead of how it's going to be used. Of course, if this is put in the car, on a car, depending on where the car is going to be used, the operating points it's going to face, the torque that is going to be asked from it, it's different. And on top of that, you have different thermal environments, different humidity environments, and it's really a big deal to try to quantify the uncertainty induced by these things. How much time did I spend on one application? Maybe I should go a little bit faster. So by the way, this is not, I like a little bit of interaction. So if you feel like anything I say doesn't make sense, I would rather you stop me and you ask me a question right there on the spot instead of waiting until everybody's asleep. All right, so this application is similar to the previous one, but it's actually less exciting because it's about manufacturing of wires. May sound stupid, but a lot of things are made out of wires if you really think about it. So it's actually extremely important to be able to manufacture wires effectively. And it is complicated because you can simulate what will happen to a wire as it passes through a die, and this simulation is actually a finite element simulation that is fed to, the result of which is fed to another finite element simulation. So it's kind of like a dynamical model that you would have to learn if you wanted to propagate uncertainty through this thing. And of course the uncertainty here is, again, in the setup of your manufacturing process. You put one die after the other, and each die deviates a little bit from the specifications, and this gives you different ultimate properties for the die, for the wire that you would like to optimize. But anyway, let's look. This was also an example of a simulation that you would like to, through which you would like to propagate uncertainties or maybe optimize. I'll give you now an example of an experiment that we have optimized, and we're actively trying to get funds for going forward with this work. This is in collaboration with Tim Fisher, who's also from Cornell, used to be at Purdue, now he's at UCLA, and two of our students, Pius and Majed. So the point here is to optimize the production of graphene, of high quality graphene. High quality graphene is in great demand, but it's extremely expensive to manufacture. And actually there's no good way to manufacture good high quality graphene at the moment, but it can be used in many different applications, ranging from micro sensors to micro batteries. So to give you an idea of the technique that a machine that Fisher constructed to manufacture graphene, I'll just tell you how it looks like. Let me just bring a few things in there. So this is the machine. It's called a chemical vapor deposition reactor. It's basically a chamber, and you pump inside this chamber different kinds of gases. One of them is methane, and methane contains carbon, and this is what is going to give you the graphene. And then you have basically a tape of a substrate, which is usually copper, and the copper rolls from a top roll to a bottom roll. So this is why this machine is called roll-to-roll chemical vapor deposition reactor. So a copper substrate rolls from the top to the bottom, and then it goes through an electrode right here that ionizes the air and creates plasma, and plasma disassociates the atoms, and the carbon atoms from the methane stick on the copper surface, and you get a thin layer of graphene. If you're lucky. If you are unlucky and you're not careful, you're going to get graphite. So you gradually roll the copper substrate through the plasma, and you gather it at the bottom roll, and hopefully with this process you can manufacture high quality graphene. So what you can control in this process, of course, is the concentration of the various gases that you can put in there, and you can put any gases you want, obviously. But we have about 6 or 7 gases that we play with, ranging from argon to nitrogen, oxygen, hydrogen, methane, etc. What else do we have? We can control the pressure, we can control the power of the plasma, and the whole thing takes, the whole experiment takes like a day to get you the roll you have here to gather it there and see what it looks like. But you cannot see. There's no way to figure out the quality of your graphene just by looking at that tape. You have to take it out and take it through Raman spectroscopy and basically look at the spectrum of whatever you have manufactured and see if it matches high quality graphene. So it's basically, you basically need to measure the output, let's say, of this function, of the function of the input to this experimental process and the output, which is the Raman spectrum. You need to have a PhD student basically set it up, go for a coffee, talk with his girlfriend or her boyfriend or whatever, and then get back and do the Raman spectrum and write the result on their notebook. But anyway, we have found a way to basically characterize the quality of graphene with two numbers. It doesn't matter what these numbers are. There's some kind of intensities with the peaks that have to do with the peaks with the Raman spectrum. And then our problem is we have a lot of uncertainty inserted into the system. Of course, we don't really know what is going on inside that chamber. As a matter of fact, the input that we provide to this experimental process is not certain. There's a little bit of uncertainty. So we say we want this pressure, but we get a slightly different pressure. We don't know exactly what we get. Also, the temperature of the whole thing is increasing over time, and this is something that we need to take into account, and so on and so forth. By the way, there's no known model of the process. We cannot model the process. It's extremely complicated. And of course, there's an uncertainty in the Raman spectrum. And then our goal was, just to give you the idea, to find the operating conditions that give you the optimal quality of graphene. And hopefully our PhD students can make a lot of money out of that. So this is another project that I have with not funded yet, but we send at least they pay the students over the summer, which is something. So this is Jesper Christensen, also from our group at Cornell, also a student of Professor Zabaras. He works at GE Global Research in Albany, New York, and he has this problem. He can't really tell me what the problem is. Okay, so I don't really know what is the function they have or the physics. And he told me that its experiment costs $10,000. And you have 5 or 6 parameters to that experiment, and they can do it, and they measure some quantities of interest, and their problem is to figure out the most important input parameters doing the minimum number of physical experiments. And as a matter of fact, the problem is to order the parameters in terms of importance. Okay, and as you can see, if your experiment costs $10,000, you're highly motivated to really think about the optimal way to select your experiments. All right. Now enough with the motivation. This is why we do all the stuff. This is what pays the bills. Now I'll tell you what we do. Okay. So we're going to introduce a simple mathematical abstraction that is usually done in this kind of work. So we have the physical model or the experiment, and we'll think of it as a function that accepts some input parameters that I'm going to call x, and spits out, so that function I'm going to call it f, and spits out some quantities of interest which I'm going to call y. Okay, we're not going to open the black box today. We're just going to think of it as a function. And this is going to put a restriction on the kind of things we can achieve if we think like that, but it's a starting point. Okay, so this is a very common assumption. All right, so using this assumption, we have 3 kinds of problems, and I'll barely touch upon both these problems. One of them is the uncertainty propagation problem. So you put an uncertainty, a probability on your inputs, and you want to see what sort of probability density it induces on the outputs. I write it like that. There's more complicated ways to write it, but this is how I like to write it. Model calibration, which is the opposite problem. You observe something experimentally that your model can predict, and you want to go back and characterize the inputs that gave rise to this measurement. And this is a classical Bayesian inference problem. And design optimization under uncertainty, which again, without loss of generality, I will think of it as a problem in which you want to maximize the expectation of a quantity of interest, expectation over everything that is uncertain, and x here plays the role of the design parameter. But of course, I'm going to show you also a problem in which you have more than one objectives. All right. In principle, all these problems can be solved and should be solved with Monte Carlo methods if you can afford to do that. It's a no-brainer. Okay, just sample the hell out of them. It works. and it's extremely easy to do, and it's extremely parallelizable, but if its sample takes $10,000 or a day, it doesn't make sense. Okay, and as Antonio Hagan put it, Monte Carlo is fundamentally unsound. And it's fundamentally unsound because its sample ignores all the previous samples that you have taken. It doesn't try to squeeze any information out of them. So what do? Well, you don't do Monte Carlo. You build the response surface, and I'll go through the classic surrogate idea. You do a finite number of simulations or experiments. You replace every occurrence of your model with a surrogate, right? Let's write it f hat, and that f hat could be polynomial chaos surrogate or just linear, generalized linear model in general, Kriging or Gaussian processes, support vector machines, deep neural networks, anything you like. Okay, just get rid of the real response surface and replace it with a surrogate. Okay, it should be cheap to evaluate, and then just sample the hell out of it. Okay, that's how it goes. Of course, there is a catch. We cannot really build good surrogates. It's not that easy. There's the curse of dimensionality, obviously, extremely important. We're going to ignore it. You're supposed to laugh at some point. The other thing that we have, the other problem that we have is that we typically need a lot of observations, simulations or experiments to build an accurate surrogate. So if you can sample if you have 5 or 10 inputs to your model and you can sample your model 10,000 times, fine. You can build a really good surrogate. Perfect. With polynomial chaos, with Gaussian processes, whatever you need. You are going to nail it. But if no matter how many input variables you have, if you have a hard limit on the number of simulations you can do, and this is what you're going to face in real applications, you will not get an accurate surrogate, period. So everything you do from that point on, if you just assume that the surrogate has a specific form, is going to be garbage, and you should not trust it to make any decisions on which human lives depend. Because people are going to die. And some other problems. We're going to focus just on that. We do work on the curse of dimensionality, but we haven't found a way actually to merge these two. I'm embarrassed to say that, but we haven't gotten there yet. So the curse of dimensionality, we typically deal with it with things like deep neural networks. This is the hottest area right now, but haven't found a way to merge the two right now. Like do fully Bayesian neural networks in a way that gives me a nice estimation of what I'm going to call in a while epistemic uncertainty. Anyway, so let's just ignore the curse of dimensionality. Let's assume that we're solving problems with 5 parameters, 10 parameters, let's say 20 parameters if we can do a significant number of experiments. All right, and here's the take-home message. Limited simulations and experiments increase epistemic uncertainty. Epistemic uncertainty induced by the limited number of simulation experiments is the key to selecting simulation and experiments. All right, so how do we quantify this epistemic uncertainty? There are more than one ways. I dare say that this is the only way that makes sense, to me at least. And it goes like that. It's a little bit strange the first time you see it, but if you meditate on it for like 10 years during a PhD thesis, it makes sense. Okay, so here's how it goes. You go to the space of your functions, to the space of your models, to the space of response surfaces, and you put a probability measure on that space. It's a probability measure on a function space. It's a little bit weird. The only requirement is that this probability measure should model everything you know about these functions before you see any data. So you know these functions are invariant with respect to certain transformations, put that in there. Do you know the length scale with which these functions vary? Put it in there. Do you know if the functions have first derivatives, second derivatives, infinite number of derivatives? Put that in there. And you have to do the homework. How you can do that? The answer is you do it on the covariance function of the Gaussian process. We can talk offline. it's extremely important for a practitioner to learn how to do that. It improves things considerably. Then you evaluate your response surface on a finite number of points, just like building simple surrogates, but you use Bayes' rule to get the posterior over the original probability measure, conditional on these inputs. So you come up with a probability measure on a function space that is conditional with your prior beliefs about these functions, what do you think these functions look like, but you only look at the nice functions that go through your data set. Okay, and then you harness this epistemic uncertainty to solve UQ problems, and by harness I mean you actually you embrace it, you keep it, you say this is nice uncertainty, I'm going to keep it, I'm going to propagate it through everything. I'm not going to select one of the response surfaces, I'll keep all of them. That's the key. And that's the guy that thought about this. Actually, this is not true. This is the guy that rethought about that after, who was it? I'm on camera, I should remember. Poincaré. Poincaré was the first person that thought like that to do interpolation. And actually, he was the person who invented Gaussian processes, but he didn't call them Gaussian processes. But this idea was popularized in the 80s, late 80s, by Percy Diaconis from Stanford, and simultaneously from Antonio Hagan. And these guys revisited these ideas to do integration, so to calculate expectations of expensive functions. So they came up with quadrature rules that had a quantified epistemic uncertainty. Alright, so the Bayesian surrogate idea, I told you, go to the space of functions. This is my attempt to visualize it. This is a space of functions, okay? This set right there. Each point is a function. So you see, it's not that hard to visualize. Anyway, so you come up with this space, all right? Now each sample from this space is a function. So if you take a sample, you're going to get one line. So what I'm doing here, just for wow factor reasons, I go to this space and I take a sample, and then I define a closed line in this space and I go around it. That's all I'm doing. Okay, that's why you see the samples going up and down. It's just moving in this space. So we basically took 3 samples and we're moving around in this space. Just because I didn't want to give you a static picture. Anyway, so this is supposed to correspond to what we know about these functions before we see any data, and we can really encode different things in these functions. Here I have encoded the belief that the functions are infinitely differentiable and that the length scale is about 0.1. And the variation is between -2 and 2. This is pretty much what I did. Now what I'm going to do is I'm going to observe this at certain places, and I'm going to grab these functions and keep them there and let them vary in between. I'm going to grab them and hold them wherever I have data. And the way I do that is by Bayes' rule. Okay, so you just go ahead and you say, okay, you guys stay there, in between you can vary. So I took my prior probability measure, I conditioned it on a bunch of data points, x and y's, and I got a posterior probability measure on that function space. And this residual uncertainty is the epistemic uncertainty because I have a finite amount of observations. Okay, so now the way you should think about that, I mean, traditional techniques like Gaussian, for example, polynomial chaos, will just give you one line. We'll tell you this line, this is the surrogate, take it and put it wherever you have to put it to do whatever you have to do. This way of thinking tells you you have to keep the whole thing, keep all these lines. They're infinite, uncountably infinite, keep them all. This is good uncertainty. We'll use it to select new simulations. Okay? How should you interpret it? Each sample is as good as any other. Each sample is compatible with your knowledge about the space and with the data you have seen. So it's good. No sample is better than other. The mean is not better than any other samples. Okay, that's the epistemic uncertainty. This uncertainty, you can now take it and propagate it through anything you want, and you can get uncertainty epistemic uncertainty estimates for any quantity of interest, that depends on the model. Any functional of the model can have epistemic uncertainty. So for example, here's the posterior. Let's say that we're interested in estimating the expectation of Rx. Let's put a probability density of Rx. So here's a probability density of Rx, and now I'm going to integrate f of x over x, but I'm not going to get a single number now. I'm going to get a distribution of numbers, because I shouldn't really just pick one of these guys and integrate it. I should pick all of them and integrate each one of them. But I'm taking the variance, I'm not taking the expectation, so I'm taking the variance. Okay? Sorry about that. So if you think like that, you will see that your prediction about the variance is no longer a single value, but it's a distribution. And that's totally okay. Of course, you want to collapse it to a point. Okay, this is the ultimate goal. You can now say, give me the simulations that will collapse this to a point the fastest, right? What is the difference with classical uncertainty quantification techniques? Well, you would get an answer, a number, but it could be anywhere here. Okay, so here the uncertainty is not dramatic, but you get what I'm talking about. Okay. So I'll just show you. Now you can propagate propagate uncertainty in this way and characterize your epistemic uncertainty in things that are a little bit weirder. For example, in this particular application, we wanted to solve a multi-objective optimization problem. So we wanted to find the Pareto front of two objectives that depend on a finite element simulation. Okay, so the Pareto front is in the space of the objectives is the set of non-dominated designs. So the question is, if you can run just 20 simulations, just 20, what is the best you can say about the Pareto front? So here's the best thing you can say about the Pareto front if you can run 20 simulations. Here are the 20 simulations in the objective space. Okay, so on the background, we use these simulations, which come with their own x's, to build a response surface, Bayesian response surface, and then we sample functions from this probability measure, and for each function, we solve a multi-objective optimization problem, and we get one Pareto front, and then we grab another sample, and we solve another multi-objective optimization problem, we get another Pareto front. Okay? And if you do a little bit of math that is a little bit complicated because you have to look at random set theory, you can use these samples to characterize your uncertainty about the Pareto front. So this red line is kind of like the median Pareto front, and then this spread is our uncertainty about the location of the Pareto front. And now the idea, of course, is to use this uncertainty to select the simulation that is going to maximize the knowledge that you can get for the Pareto front. I'll make this precise in a while. And of course, we can do that. We have done that also for the, this looks actually a little bit nicer. We have done that for the graphene growth paper. Oh, this is published work, so you can go ahead and look at the math. If you, it's a little bit scary, okay, but it's not a big deal. You can give me a call. All right, so let's go to the, now that we know what the epistemic uncertainty is all about and how we can propagate it through quantities of interest, let's ask the following question. How do we select which simulation or experiment to run next? And this is the key. Use epistemic uncertainty to construct information acquisition algorithms. This is the key. And I'll give you two ideas. All right, let's start with what everybody starts with. Let's just start picking the simulation about which we're maximally uncertain. So you see right here, the red dot is the point about which I'm maximally uncertain, the point that has the maximum predictive variance, and this is what happens if I select that point. So you see that uniformly you improve your state of knowledge about the underlying response surface to the point where you have actually nailed it. The catch with this is that this is okay, you should do that if what you want to do is learn the response surface. If that's what you want to do, if you want to learn the response surface everywhere, this is actually optimal. And it is actually the answer you're going to get out of one of the generic criteria that I'm going to introduce later. For this Gaussian process, the design is known before you start, so you should think a little bit before you start doing it. It's actually simpler. But anyway, what if you want to learn, I told you that this is not optimal, it's only optimal if you want to learn everything, but what if you want to learn a specific thing, like a quantity q that depends on your function f, like the mean of f, or the variance, or the probability that f exceeds a certain value, or the maximum, the point that maximizes f, or the Pareto front of two objectives. Yeah, I guess this is all I've said. Or even other things like the posterior distribution of an inverse problem, etc., etc. Or the order of sensitivity indices, which is what we do with GE. When Sapsis comes here, Themis, maybe he talks about that. This is his most recent paper. He actually published it also in the SIAM review, right? The newspaper of SIAM. So this is also a very hot area. All right, general idea number one. I'll give you two general ideas. Which one you use depends really on what you want to do. Okay, so here's the first idea. Collect data in order to maximize the expected information gain about Q. Obviously. What else would you like to do? That makes sense, right? Maximize the expected information gain. Of course. Who wouldn't want to do that? This may sound vague, but it's actually a very precise mathematical statement, which I'm going to show you right now. So here is the quantity of interest Q, which is any functional of your underlying model. And if you use the data you have so far, input-output observations of your function, this is what you should currently think about Q. So this is your posterior predictive distribution for this quantity of interest given all the data you have seen. Now you ask the hypothetical question. What if I go at X and observe Y? What if I do a simulation or an experiment at X? And what if the result of that experiment was Y? How would my state of knowledge about that quantity of interest Q change then? So it would change, let's say, to the red line. Hopefully, it will shrink a little bit because now you have a little bit more data. All right, so you say the information gain is the difference between these two distributions. And I mean, I'll take the information gain to be the Kullback-Leibler divergence. When Themis comes here, he's going to take it to be a norm, a distance between the two distributions, an actual distance, which is actually a little bit simpler to calculate for his particular quantity of interest. But I'll take it to be this. The Kullback-Leibler divergence between the red, I guess, you're colorblind, right? Red and blue. And here's the catch now. You have the Kullback-Leibler divergence, which is the difference, the information gain as you go from the blue to the red, but the result of your hypothetical experiment, you don't know what it's going to be, so you need to integrate it out. So you use your current state of knowledge, your predicted distribution, to take out this Y. Okay, so you integrate out over what this Y can be. So you have here the information gain of a hypothetical experiment, and you're taking the expectation over what the result of that hypothetical experiment can be. So this is called the expected information gain. Your Gaussian process is here, and of course here and here. And okay, it looks simple because it's one line, but it's actually not trivial to evaluate it. It requires significant amount of effort for every different Q that you put in there. Let's just say that. Now here's the thing. If the Q you choose is the parameters of your model, then you can show that this thing is going to be it's going to be basically proportional to the predictive variance of the Gaussian process. So this theory tells you that if what you want to learn the most about the parameters of your model, you should maximize the predictive variance. You should select simulations that maximize the predictive variance. So it tells you if you want to learn the response surface, maximize the predictive variance. That's what it tells you. But you may want to learn something else. Okay. Just to give you an idea, we are deriving what these things should be for the order of sensitivity indices for about 10 months. And we're getting there fully. All right. General idea number 2. This comes from economics. So you collect data in order to maximize the expected value of information. Okay, but of course this comes with a catch. You have to quantify what you mean by value of information. It goes like that. You have to say first how much value you have obtained so far from your experiments or simulations. Okay, so let's say that, let's call it V of D, and we are going to subtract the cost of doing these simulations. Let's say that you are actually designing something, right? Let's say you are designing something. This would be the cost of doing prototypes. And that will be the net present value of all the cash flows that are coming to you from the sales of the product, if it has specific properties. But it could be simpler. You could just make up you can measure the value in your own currency. And then you ask the following question: how much additional value will I get if at X I observe Y? So let's do a hypothetical simulation experiment. It gives us Y back. How much value are we going to get from that? So you have to quantify now this value. So if I add to my set of observations X and Y, then this is the kind of value I'm going to get. This is how much it's going to cost me to do this experiment. And this is the value that I had before. So this is the difference value. So this is how much I'm going to increase my value if I do a hypothetical experiment. But of course the experiment is hypothetical. This Y, you don't know what it is going to be, so you have to integrate over what that Y is, and this is the expression you're going to get. So this is what I call the expected value of information. So here's how this goes. If you make some very, very crude assumptions here about the value, if you say the cost of acquiring data is 0, the value is of observing the function value is the function value itself, then what you're going to get here is known as the expected improvement. Or it's known in the engineering literature, the algorithm you're going to get is known as the efficient global optimization, or EGO algorithm. If you do a less crude approximation, you would get the so-called knowledge gradient, which is what Peter Fraser works on at Cornell Operations Research. It's an extension of the expected improvement. So you can derive all these from these things. And of course, it is not trivial, right? You have to come up with a semi-analytic expression or approximation of this integral to be able to carry this project out. Now the good thing about including the cost is that you can use the cost to select different sources of information. So the cost is what characterizes the difference between a low fidelity simulation, a high fidelity simulation, or an experiment. So this kind of thinking allows you to select between different information sources. All right. So this is the generic information acquisition paradigm. So the idea is to come up with an information acquisition function that matches whatever you want to learn from your simulations or your experiment, and then sequentially add the simulations that maximize, or experiments that maximize this information acquisition function. And I introduced two of these information acquisition functions, the expected information gain and the value of information, and they both relied on the concept of epistemic uncertainty. This is not the optimal thing to do, this is a heuristic, because in reality, if you really think about it, The real problem is this. The real problem is find a policy that maximizes the expected information gain or the value of information. This thing looks only one step ahead. In reality, you should look as many steps ahead as possible. You should consider the optimal stopping problem, which is a very hard dynamic programming problem. I know of only one person that has attempted to do that, and that would be Karen Wilcox from MIT. But for the rest of us, because this is very hard. This is so hard that if you pose it the right way, it's going to be harder than doing the experiment. So at some point, it doesn't really make sense to go to seriously consider that problem. It's better to go with a heuristic, because you should, in reality, you should also include in your calculations the cost of paying somebody to come up with all these things, okay, and then actually solve this problem for a selected simulation. If this is ridiculous, then you know you're back to square one. All right, very hard, but may pay off. It will pay off if what you have to, if your experiment is really, really, really complicated, really expensive. All right, so here's how it looks like, the complete picture. You have some simulation experimental data. You use Bayes' rule to characterize your state of knowledge about the space of response surfaces that may have produced this data set. And then you use the epistemic uncertainty you propagate the epistemic uncertainty through to any quantity of interest. And then if the epistemic uncertainty is acceptable, or if the value of information of a new simulation experiment is very low, you stop. Otherwise, you select the simulation experiment that maximizes the expected information gain or the value information, and you perform that experiment and you put it back in and you repeat. And of course, there are many extensions of this thing. For example, you may tell me, you know what, actually I should do experiments in parallel. I have supercomputing facilities that allow me to run 10 simulations at the same time, and I will tell you, no problem, just go here and maximize the expected information gain of 10 simulations, or the value of information of 10 simulations. You just have a harder mathematical problem to solve, that's all. Do I have any time? Okay. So this is an example of an optimization problem, a 1D example, basically, toy synthetic example, where we maximize the problem is to maximize the expectation of a function, and I use the value of information to do that. And you see here noisy evaluations of that function. So the real problem in this particular example was the fact that it was supposed to emulate an information source that is experimental, and every time you evaluate it, you get a different result even at the same point. So we retained a lot of experimental noise, and the problem was sequentially select simulations in order to find the minimum of the expectation of that experiment over the experimental noise. Okay, but filtering the noise along the way. So what you see here is the observations, obviously. The shaded area is the 95% prediction interval of my underlying Gaussian process. This line here, right here, is the value of information of any one of these simulations. The dashed line is actually the truth, the true underlying expectation. And you see now the simulations that the model selects, and it's actually, at the beginning, it explores a little bit of space, and then it figures out that the minimum is somewhere here, and it starts to completely ignore this space. And if you notice, and this is the important thing, it doesn't really care about learning the function here. It doesn't care. It's like, I know the minimum is there. Who cares about this part? Forget about it. We're wasting simulations. Let's just concentrate there. So after an initial period of exploration, it concentrates here and it tries to resolve the expectation. But this is 1D, okay? We also did it in 7D with a real experiment with Fisher for graphene manufacturing. Unfortunately, I don't have a video for that. But I can show you the kind of experiments that originally we started. This is the performance metrics, and the lower the better, and there is noise here. So the fact that that this point is there doesn't mean that it's really there. It may be anywhere up and down. So originally we started here at our first experiments at this region, and then we selected experiments that maximize the value of information for the Pareto front. And this is the Pareto front you can see here. And eventually we got, so this is the graphene that we were getting originally. And then as you go down, you start getting better and better graphene. But here we have reached the limits of this particular manufacturing process. So it's still not perfect graphene, but it's at least the, let's say, imperfections are less. Anyway, so this is pretty much it. I like to keep it short. So the original core, let's say, fundamental research on that came from Cornell and my collaboration with Professor Zabaras. So these are my thesis papers. And we mostly worked on uncertainty propagation then. And we went back and forth. Of course, if I knew now everything I know, if I knew then everything I know now, we'll do probably more. But I guess this is in the process of doing your PhD. You have to go through a steep curve of learning curve at the beginning. And this is the continuation of this work. I mean, it took we have a gap of 2 years until the students start to pick up. But now we're very productive on that, and we applied it also with Professor Zabaras and Jesper on the selection of simulations for learning phase diagrams. Yes, and we're moving on. So if you want to know more about the idea of selecting simulations for solving a multi-objective optimization problem, this is the paper, and it's on arXiv, should be published soon. And with that, I finish. Okay. I'll take any questions you have, related or unrelated to this. Yes?
So I'm thinking about the comments you had about designing a batch of experiments. In the case where you're designing just the next experiment, you have some dimension to your input space that you're searching over.
Mm-hmm.
However, when you're thinking about placing multiple points in there, we have a set of coordinates for each of those experiments, and it would seem that would make the dimensionality of the search correspondingly larger.
Yes.
Can you comment about some? Do you have any thoughts about that?
Yeah, definitely.
Can you briefly repeat the question for the microphone to pick it up?
Yes. So the question is when you maximize sequentially the expected information gain or the value of information for a batch of hypothetical simulations or experiments, the optimization problem that you get may be so hard that you cannot actually do it. This is absolutely true. I mean, I simplified it a little bit, but that's in essence the same thing. Yeah, it's absolutely true. It becomes very hard to the point where you cannot do it. And that's exactly why it is interesting, because you can actually write a paper on that. And there are several heuristics that you can introduce in order to solve it. One of the heuristics that I know that works, and it was actually introduced by Robert Gramarcy from University of Chicago, Booth School of, is it called Booth School of Economics? Business School, yeah. So this guy said the following thing: I want to do many simulations. He works on simulations. I want to do many simulations at the same time. I cannot really optimize any of these criteria for a batch of simulations. So here's what I'm going to do. I'm going to select the best simulation, Okay, and then I'm going to pretend that the result I'm going to get from this simulation is the expectation of my Gaussian process. I'm going to put it in there, and then based on that, I'm going to pretend that I have it, and I'm going to select the next one. Okay, up to the number of batch points that I can do, and then as the simulation start coming back, I'll go back and I get rid of the hypothetical value, the value that I just picked, right? And I replace them with the right values, and I will repeat. And that works quite well. And actually, we actually did that for the Fisher experiment, because it turns out that we could do 5 or 6 experiments at the same time. Excellent question. Yes?
So I have a question related to constraints, inequalities.
Mm-hmm. Yes, perfect.
How difficult it is to, put them in. Many times when we build surrogates, we might violate physical laws. The missing information in the data and the limited times we can sample also might, violate certain constraints. Or there are just physical constraints.
Yes.
In terms of how to get all of this executed. And inequalities are non-smooth. They bring a lot of complexity. How difficult it is with inequalities?
All right. So your question has two. I can apply it to two concepts. Okay. So one problem, and pick your favorite one. I will answer both, but you can pick your favorite one to be answered first. One is when you're building the surrogate. If you know that your surrogate should satisfy certain physical laws, can you enforce these physical laws? This is question number one. Let's answer this first. The answer is that kind of. Okay. So I'll give you two ideas. First, you should struggle to make sure that if you can do some physics, you should do some physics. If you know that the functions you're looking at are invariant with respect to some symmetries, you better try to build this symmetry in. One way to do that is to play with the input. So if you're doing, for example, you want to learn the energy of, let's take a specific example. Let's say you want to learn the energy of a molecule, okay? And you're using as x the Cartesian coordinates of the molecule. Now you know that the energy is going to be invariant to translations and to rotations of your coordinate system. Okay, so it is better to work, instead of the Cartesian representation, to work with the distance matrix, because then these invariances are built in. But there are also more invariants that you could exploit. For example, if you have a molecule and then you have a hydrogen atom there and a hydrogen atom there, you can actually swap their labels. You can call this hydrogen atom 1 and this hydrogen atom 2, or vice versa. And your energy will remain invariant. So the energy surface will be invariant to permutations of atoms that are the same, of the same type. And you can actually come up with a representation that satisfies these invariances. You can come up with monomials that automatically satisfy permutation invariance and